All right, so in question 6, this was the first of the long answer questions. We're told, this is a question very similar to one of the questions that we did in class. In class, we had a rope pulling up on a person that wrapped around a pulley, wrapped around another pulley, and attached to the elevator. And the person pulled up their weight by pulling down on the rope. And so here we have a person attempting to lift an elevator she's standing in by pulling down on a rope that passes over a pulley attached to the ceiling and is connected to the top. The pulley is connected to the top of the, the rope is connected to the top of the elevator. We're told to treat the string and the pulley as massless and the pulley as frictionless. And that's keywords for saying the tension is the same throughout the rope. So in the first part of this question, we're told that the elevator weighs 25 kilograms, she weighs 60 kilograms, and asked how hard she must pull to lift the elevator and herself at a constant speed. Constant speed tells us right away that the net force acting on the system is equal to 0. This is an interacting problem, so we've done quite a few interacting problems. And we know that for interacting objects, we need to draw 2 free body diagrams, and that we're going to likely have action-reaction forces on both of these free body diagrams in opposite directions. So let's draw 2 free body diagrams. We want how hard she must pull. So the force she's pulling at should be equal to the force that the rope is pulling up on her, which is called the tension in the force. So force pull on rope equals tension, which is force rope pulls on her. So we have 2 objects here. One of the objects is the elevator. The other object is the person. And we know that in both cases we have net force 0. The elevator has a weight. Let's call that weight of the elevator. The person has a weight as well, which is a larger weight. Weight of the person. The person is pulling down on the rope, which causes the rope to pull up on the person. And so we're going to call that a tension. And then the person's also standing on the floor of the elevator, which means that there's a normal force acting from the floor of the elevator upwards on them. And so this is a normal force from the elevator acting on the person. Now, if there's a normal force from the elevator acting on the person must be pushing down on the elevator. So there's another force here on the elevator, which is the normal force of the person acting on the elevator. And there's a tension that's pulling up on the elevator as well. And these 2 tensions are equal. So in this part, we're asked to find what the tension is in this problem. So let's call this y, call this x, y, x. And in both cases, F net is equal to 0. So this is a problem in linear equilibrium, using Newton's second law for actually dynamic equilibrium. So in this problem, we've drawn a free body diagram. We need to write Newton's second law in component form. For the elevator, we have T, the tension, take away normal force of the person on the elevator, take away the weight of the elevator, is equal to 0, because there's no net force. And for the person, we have tension of the person plus the normal force of the elevator acting on the person. Take away the weight of the person is equal to 0. And we know from Newton's third law, normal force of the person on the elevator is equal to the normal force of the elevator on the person. Looking at these two equations, if we want to find the tension, we could add these two equations together because these two normal forces are equal, but they come in with opposite signs. And so we could say, add those two equations to find 2t, 2 times the tension, take away the weight of the elevator, take away the weight of the person, take away the normal force of the person, plus the normal force of the elevator on the person. These two things add to 0, and this whole thing is equal to 0. So 2 times the tension is equal to the sum of the weights of the elevator and the person, which is the mass of the elevator times g plus the mass of the person times g. We can substitute in for those weights at this point. 85 kilograms is the sum of the masses of the elevator and the person, and those are both multiplying by 9.8 meters per second squared. And so tension is equal to 85 times 9.8 divided by 2. So we put 85 times 9.8 divided by 2 equals, and we find 416.5 newtons. So 416.5 newtons, or 417 newtons, is what the tension is, while she moves upward at a constant velocity of 3 meters per second. What apparent weight does she have? So the way I would measure apparent weight, and probably the way that you would measure apparent weight, would be to say, well, this person has a weight that they would measure in the elevator if they put a scale underneath them. So put a scale under to measure apparent weight. And so that would mean that the reading on the scale, our apparent weight, would be the force that's pushing up on us from the bottom of the elevator or the scale. And so what we're looking for here is the normal force. The normal force is something that we can solve from either of those two equations. So we want the normal force, tension, take away normal force, take away weight of the elevator is equal to 0. We know what our tension is, we know what the weight of the elevator is. Rearranging this equation, normal force is equal to, normal force go to the other side, tension, take away weight of the elevator equals 416.5 newtons. Take away the weight of the elevator, 25 kilograms, times 9.8 meters per second squared. So we take out our calculator, 416.5, take away 25 times 9.8 is 171.5 newtons. We could also have used the other equation, and we would have found the same thing. So if we add 416.5 to 171.5, and we take away 60 times g, which is the weight of the person, then we would actually get 0.